Welcome to Supply Chain Next with your host, Richard Donaldson. Join us as we explore the ongoing evolution of supply chain, from the challenges professionals face every day to the ongoing digital transformation of the entire value network.
And welcome to the next episode of Supply Chain Next. And I am super thrilled today to have Ryan Hunt on here. Good morning, Ryan.
Hey, Richard. Thank you for having me.
Absolutely. And, Ryan, I think, you and I got a chance to speak not too long ago here, but I think what's so fascinating about today's episode, what I'm super thrilled about, is the work that you've, kind of grown into, but in the area of algae, basically, and using that, in the context of circular economy, reusable materials, and some of the stuff that I've seen that kind of ran across here, the transom, is what you've been able to create, even in the context of 3D printing and powders and whatnot. So really, really fascinating topic to get into. I think it's super timely, and it's somewhat interesting in that I think it's kind of overshadowed a little bit by some of the carbon and other things people are chasing, which may or may not result in circularity and sustainability. But what you're doing is absolutely in the bullseye of sustainability. So super thrilled to have you here today. And so let me just start. I've been rambling for a second there, but Ryan, maybe just give a quick intro, kind of who are you? Who's Ryan Hunt? Where are you from? How'd you get started in all this stuff? Because probably didn't start as a kid thinking I'm going to get into algae and all things ocean.
No, I've always been into technology, but certainly the algae angle started in grad school. So again, I'm Ryan Hunt. I'm the co-founder and chief technology officer of our company ALGIX and our brand Bloom Sustainable Materials. We work with governments and utility companies to use algae as a tool for environmental restoration. So we'd like to clean water, absorb and capture CO2, and use that biomass as a replacement for petroleum-based plastics and consumer products. So by using the algae as opposed to oil, we're able to improve the environmental metrics that are defined by what's called a life cycle assessment. And we take the data that comes out of the LCA or life cycle assessment, and we use that to quantify the benefit of switching out petroleum for algae. So algae is renewable. We're using it in a way that we're recycling the nutrients, this kind of circular approach of taking the pollution from factories, from utility companies, from industry, from agriculture even, and using that as a nutrient source to grow algae. And then from that restoration process, we then now have a biomass that we can directly replace, to some extent, the use of oil in consumer products. We've been focused on footwear. We've got over 130 brands, footwear brands. Our biggest customer is Adidas or Adidas, depending on what part of the country or world you're in, and Easy and Merrill and many others. So we've got a whole host of great partners that are, putting sustainability first at their companies, trying to find ways to incorporate sustainable materials. But, really for me, it started as a biofuel project in 2006. I was working on using Chick-fil-A fryer grease to make biodiesel. Who doesn't
like Chick-fil-A? Before I even go any further, I mean, right there is, if there's just a small little pop for Chick-fil-A, man, that chicken sandwich, it's good.
Yeah, you can't go wrong there.
Before you go into that, Ryan, let me ask you to back up just a little bit further. So I think you've also got an interesting kind of story from, well, I'm not going to go back to birth or inception, but where are you from in the country? And then kind of, walk a little bit through, because again, your path is interesting. And especially we have a lot of people who tune in that range from people who are in undergrad all the way up into the graduate, thought leaders. Then you're obviously a thought leader, but, since algae, I think, is on the horizon, no kidding, something that's really coming into the forefront. A lot of people who might be in their undergrad programs hearing this or listening to this might be, tuning in and going like, what is this algae thing going on here? Like, how did you kind of move from getting in, even in high school, into college, and then ultimately into this? I mean, that's kind of an interesting tale on itself.
Yeah. So I'm from Atlanta, a suburb of Atlanta called Marietta. And I went to college at the University of Georgia in Athens, Georgia. And I've always wanted to be a physicist. So in high school, I took AP physics. I declared my major a freshman in physics. Just always liked the concept of thinking about technical problems at the first principle levels. So what are the fundamental issues? Dial it down to the simple mathematics of any problem. So that's kind of how I've been trained to think. So that's how I have approached these challenges. I was actually kind of heading down the route of electric cars in like the early 2000s, 2002, 2003. At that time, it was too early. I probably should have stuck with it. I probably could have been, working a hype at Tesla by now. But, that was who my heroes were back then. Were like, the very, very beginnings of when, Elon Musk bought AC Propulsion and kind of got me into this realm of alternative energy, renewable energy, and sustainability. For me, started with electric cars, actually.
Right.
But
just a quick clarification there, because in physics, and I mean, there's a bead I'm drawing the string here too. In physics, you can either go big objects or small objects. And if I'm hearing correctly, you went down into the small kind of quantum-y level.
I was really interested in quantum and nano. That was kind of my angle in modern physics as well. And so I had a lot of interest in electromagnetics and the effects of electromagnetic propulsion and effects of electromagnetic fields on biological systems. So that was actually kind of what got me initially kind of crossing bio and physics together. I wanted to get my PhD in biophysics, actually. That was like my goal. Didn't quite turn out that way. I got kind of sidetracked in this whole algae front. So I started, as I mentioned earlier, I was starting with making my own biodiesel, just because I thought it was cool to be able to like produce our own fuel. This was like in 2005, 2006. So oil prices were like really skyrocketing at the time. And then from there, I went to a biodiesel conference and met a guy from the university who was running the engineering program and the outreach. So he said, "Hey, we're looking for a grad student, undergraduate student to come work in the lab." And so one thing led to another. Next thing you know, I'm hired as an undergraduate, still in physics, but working part-time in the bio and ag engineering department, focused on turning pine trees into crude oil. So the first 9 months of my of this career ultimately was actually still in school, basically working for a postdoc, characterizing bio-based oils that were produced from trees, from pine trees. And so that was the initial project. And then that kind of led into, well, if we can turn trees into oil, trees grow real slow. What's the fastest thing that grows? Well, the fastest, most photosynthetically efficient organism is algae. About over 30,000 species of it. Some of it grow faster than others, but there's certainly a variety of strains that have these incredibly fast growth rates. They don't have to produce stems and roots and branches and bark and flowers and fruit. So all the energy that they absorb, they turn directly into reproducing itself, duplicating itself.
And just to put a finer point on that, somewhere in there, people were, again, the problem that you sort of jumped into, and it's a big one, was what can we use as alternatives for oil? And people were kind of playing with all these quote unquote sustainable materials. And somewhere in there, even though they were focused on trees, someone came along in the midst of all this and was like, hey, wait a minute. There's all this material, this biomaterial called algae, right? I mean, shit, we came from the water. Why can't our energy come from the water? And here's this material that's, in abundance. Is that who kind of like sparked that, or was it just sort of the natural progression for you to dig into the materials as you just outlined?
No, it's okay. Funny story. So really it was twofold. I was already growing algae inadvertently because I had five saltwater aquariums in college. So I had a bunch of aquariums and I was battling algae blooms literally almost every day. I mean, every weekend.
And this was just to keep your fish alive. It wasn't necessarily that you were interested in biofuel. You were just like, holy crap, this stuff.
Christmas, I left town for Christmas to go visit my dad, and I was gone for a week. And the algae bloom got so bad it killed one of my tanks and killed two of my favorite pets. Oh my God! I had a big moray eel and a big triggerfish, and and so they died because they had an oxygen depletion event. The algae got sucked up into the filter and clogged the filter, and the whole thing went down. And my roommates didn't know what to do and didn't really recognize it at first until it was too late. And so, anyways, so that was my first personal fish kill was from algae bloom in my apartment in college. And I was like, well, that sucked. Like that, I just cleaned that tank before I left. In a week, it went from I mean, somewhat clean to like killing everything. So, so I started looking at, well, how fast, like, how does this stuff grow so fast? And then that's when I started doing research. It was like, well, it turns out like algae grows really fast. It can duplicate and double itself in a day or two. So you clean it out all the way, you know, you leave 10% within just a few days, you're all the way back up to almost where you were. So basically that was the initial stimulus, was dealing with it personally. But then once I got serious and started looking into it, the federal government from 1970s to 1990s had a program called the Aquatic Species Program. And this was a multi-million-dollar funded research program with the National Renewable Energy Laboratory in Golden, Colorado. And they were basically researching algae-based fuels and biodiesel and ethanol for over almost 2.5 decades. So that whole 300-page final report was available online. I downloaded it. I printed it out. That was my nighttime reading in 2006, 2007. So once I saw that and started reading through all the more peer-reviewed fundamental research, it was like, all right, yeah, sure, I got a fish tank full of algae, but turns out there's a big opportunity here. You know, algae is one of the most ubiquitous organisms on the planet. It's all over. It's in every water, every ocean, every sea. It's in the soil. It's in the Arctic. It's in the equator. I mean, it's everywhere. It's actually one of the earliest organisms on the planet. It's been around for somewhere, they think, around 3.5 billion years. So it really is one of the major predecessors that changed life on Earth by delivering oxygen to our atmosphere. So it's this very, very important class of organism. Yet as humans, we have really yet to use algae in any productive way. And certainly back in 2007, I mean, it was just kind of the early days. So there was a big resurgence in 2007, 2008, and kind of up till about 2014, really, where, you know, hundreds of millions of dollars got dumped into algae startups, algae research and grants. Department of Energy, DARPA was putting money into this, really focused on biofuels. What ended up happening was that scalability was the challenge and oil price fluctuations were the challenge. So while the price of algae oil did come down and did drop, and there was a lot of improvements and was a lot of innovation, it still was relatively expensive, and it required a lot of capital to build up to get the cost down. And so, you know, no one was really ready to drop $1 billion on an algae farm yet. Some people dropped to 200 million, like, you know, Sapphire put, I think $200 or $250 million into their 300 acre facility out in New Mexico. So there was some of that starting to happen, but really as it started to like kind of come to a precipice in 2014, the oil prices collapsed again. And when the oil prices collapsed, basically biofuels dried up. And then for us, even the plastic prices dropped big time. So for polymers,
but you're describing a similar problem that most renewables have had, right? It's not a question so much, and we always talk about cost, but if you peel the onion even a little bit further, it's actually scale, right? I mean, which is truly what drives the cost down, and unfortunately, people are right. Exactly. It's not that the cost will be driven down as you scale something up. Renewables like solar, even car batteries like lithium, right? I mean, that's until we hit certain scales, right? The pricing parity against existing systems was not fair. So like there's sort of like a ramp up time you have to allow something to get to that our impatience as a species prevents us from doing what's the right thing, even though it's obvious.
So I even made a chart to try to help people kind of conceptualize this. And I think that the folly that was made in the early days was that we were going to be able to scale basically infinitely big, infinitely fast, and deliver to the cheapest product on the planet, gasoline, right? Gasoline is like our combustible fuels are, we think they're expensive. They're really cheap, especially when you look at it on a weight basis per pound. I mean, a gallon of gasoline weighs about 7 pounds or so, 7.5 pounds, right? It only costs, $2 to $4 or $5 per gallon. So you're talking about sub $1 per pound, 50 cents per pound or even less for a pretty complicated product that's distributed around the globe. So that has to meet all these very, very pure specifications. So getting algae to deliver that at that price range and with the stability and the robustness of those price fluctuations, it's really hard. So we said, early on, we saw two fundamental issues. One was that when the algae is blooming, when there's a bloom of algae, which would mean that it's growing in this exponential growth rate, it's absorbing nutrients, it's gobbling up CO2, it's doubling itself rapidly. When that happens, the biomass that grows does not have a lot of oil in it. So this whole concept of growing algae super fast and then taking all that algae and turning it all into fuel, just right off the bat, it's not really good. It's not really how it works. The easiest way to do it is to have a species of algae that naturally contains oils that are conducive to being converted into fuels, like triglycerides, fats that can be transesterified into biodiesel, as an example. To get that, normally you're looking at best case 20% yield. So 80% of your algae that you're growing is not part of the fuel equation to begin with. Then you got to get that 20%. You got to refine it. You got to purify it. You got to transester. Like all this processing goes along to get it into the right form to be able to use in a car engine. That takes time, money, effort, energy, et cetera. So we kind of saw that as like, all right, yes, maybe that could work, but let's focus on the 80% fraction. What are we going to do with all that biomass that's left over? A lot of people are focusing on how to make the oil and how to make the fuels. Maybe that'll come to scale. But if we don't figure out what to do with the 80% fraction and how to cross this chasm of death to find a market that doesn't require super, super, super cheap products, how do we get more value out of that material? And so that's when we started looking at animal feeds, at fertilizers, and ultimately at materials. And so the materials one really perked my interest because as a physicist, thermoplastics and materials, a lot of it's physics, it's thermodynamics, it's chemistry, it's physics. And so to me, I understood it. I was like, all right, I could read the research papers and grasp what they were trying to do and what the properties were. So when you start looking at a material, the simple equation is that it's a lot more valuable per pound compared to gasoline. It could be 5 times more valuable per pound than gasoline. So right off the bat, you're 500%. But
the value you're depicting, though, I'm almost seeing like a pie chart of all the different use cases. 20% might be actually using for combustion engine. And by the way, I'm going to footnote that one because there's a question. I'm going to come back to that. So maybe it could be used for, combustion engine type things or combustion in general to generate power. Or these other 80% of the algae could be used for different things like actual materials, like a replacement for plastics or things of that nature. So therefore, whereas when we look at gas or oil and its refined products, it has one use case pretty much.
Yeah.
Both.
Yes.
Right.
I mean, when you have a barrel of oil, there's a lot of that oil that does go to polymers. I mean, it's not a huge fraction. The majority does go to fuel, but there's a chunk that goes to polymers. So, but the per pound price of a polymer, with gasoline, maybe it's 50 cents, on a good day. We're talking about $1, $2, $3. In some cases, we're getting up to $5 per pound.
Wow.
So that's up to 10 times the value of the raw material. And but that only works. So then when we looked at taking the algae into materials, it's like, all right, well, polymers is this massive field as well. There's cheap polymers, there's expensive polymers. So what do you want to play in? There's polymers that have high volume and high market, and there's small, and there's niche stuff. So as a startup, you always want to focus on niche markets to start with, just because the big commodity stuff is too cheap, it's too competitive, it's too big. Focus on niche. But us really not knowing that much. I mean, we kind of came in as complete newbies into this market. I'm not a polymer engineer. I'm not a polymer scientist. I'm not a commercialization manager. I'm a scientist. So we looked at it and said, all right, let's take the algae, let's blend it. And we started making these compounds that are half algae, half polymer. And when we did that, we were able to get much better material properties from the algae that kind of mirrored or mimicked the base properties of that polymer. And so we selected kind of like 4 major classes. We selected the cheap commodity polypropylene that is used everywhere. It's the workhorse around the world for plastics. And we were able to blend algae with polypropylene. We were able to blend algae with polyethylene, another workhorse across the industry, as well as recycled versions of polyethylene. We then were looking at bioplastics. What if we wanted to get into packaging? So we started blending algae with PLA. PLA is a corn-based or sugarcane-based polymer that's used in packaging and other applications. So we were making some injection moldable parts, mostly for, at the time, flower pots was kind of our goal, was being, okay, we're making biodegradable flower pots. It just seemed like something easy to make to prove the concept. So we were making PLA. And then the last one was kind of a wild card. We just picked it because of the spec sheet. I didn't really know much about it, but it's a material called EVA. It stands for ethylene vinyl acetate. Most people have never heard of it, but I would guarantee you're probably wearing it right now. It's the flexible foam that's used pretty much in every sneaker in the world.
Oh,
so if you have a sneaker, if you have a tennis shoe, if you have an athletic shoe, or even many casual shoes, or even flip flops, they're made of EVA. And EVA is made of 80% polyethylene. A run-of-the-mill, one of the biggest plastics in the world, mixed with a little bit of what's called vinyl acetate, which is it kind of helps it get flexible and rubbery. So it gives you this flexible foam, but it had a lower melting temperature and it had this polarity that made it compatible with the algae. And so we started blending with EVA in the very first trials that we did, not quite realizing what that would turn into, but just picking it because it played well with the algae, and we could make cool we could make these cool dog bones. Here's a dog bone that I made in like 2011. So it's pretty old.
My dog needs one.
Yeah. And, so like that's 50% algae, and it still feels and performs and lasts. Like the durability is as good as the normal EVA for the most part. So now if we did the same part in PLA, it would be biodegradable. It would be compostable, and the algae accelerates the rate of degradation. However, what we found was that in the early days, we were very much focused on bio-based materials. And it was just, for us commercially, it was tough because no one really wanted to pay more. Bioplastics always cost more. And B, they had a specific performance specification that needed to be met. And we're very limited in the types of performance that these bioplastics currently are offering. So we never were able to hit the spec. And when you can't hit the spec, if your product doesn't mechanically perform to their needs, the project's done. So we struggled for years trying to get these biodegradable compounds out into the market. We failed. We never were successful to do it. It wasn't until 2016 that we started talking with Nike and Adidas that things really started to turn around. They said, "Oh, you can do EVA? You can do foams?" Like, yeah, sure. Like, we can try that. We can explore that. We know EVA works well. And so Adidas started opening some molds for us in Asia at some of their partner factories. And we got real excited. We're like, all right, this is going to be great. We're going to go we're going to get a big purchase order from Adidas. And, we're going to we're going to make it across the chasm of death, and we're going to be a successful company. And we're actually going to do it. So we all got excited in 2016. Then like the reality struck. That's like, oh, wait, Adidas doesn't actually make anything. They design stuff, they market stuff, they distribute stuff, they do a lot of stuff, but actually making shoes is not one of the things they do. The majority of the shoes, basically the vast majority of shoes in the world, they're all made by independent, third-party, Chinese-owned factories, right? Vietnam started getting some more kind of over the past couple of years, but then with last year with COVID shutting down Vietnam for a quarter, a lot of that business has flown back into China. It's starting to trickle back into Vietnam. But either way, whether it's China, Vietnam, Indonesia, that's where the production's at. And it's not, and those aren't factories that are like, it's not like it's a Nike factory or it's an Adidas factory. These are factory names you've never heard of, right? And so, so kind of getting into the supply chain part, we had the rude awakening that's like, oh, this is going to be way harder than just signing a PO with Adidas. Like it's not that easy. So we then started going to China. We set up our own wholly owned foreign entity. We hired local footwear professionals. China nationals, and we started working with these factories. It took us about a year to get the first factory to say yes to work with us. It was really hard. Nobody really wanted to do business with us, and nobody really wanted to buy our material. The brands had to demand it, that their factories used it. And then we had to kind of go to the factory and, shake the hands and drink the tea and drink the baijiu and do the whole dance to get, build the trust with these guys, which started. And then after we got the first factory, the second one was a little bit easier. Third one, a little bit easier. And then it started to snowball. And then as more and more brands started asking about it, like the whole floodgates opened. And right now we're over 400 partner factories.
Wow.
That are buying, or at least have at one point purchased our material and used it. Now, not everybody's active. We've got probably a couple dozen of factories that we consider our preferred factories. These are the guys we have the most relationship with, the most trust. They've done the best job. They're competitive. They're fair for the most part. So, or at least as far as we can tell, because we can't really go there. So. All right.
But so, timing. One of these things again here is timing, because if you did this 20 years ago, I don't know if you'd have this success. And then there's persistence, of course, right? Sort of chance favors the prepared. But let me circle back for a second, and we're going to come back to where you're at, which is I'm going to go into your particle physics kind of a little bit here. So one of the things when I look at the system here is we are looking for, we always talk about oil and renewables, right? And oil, for lack of a better term, is a material that we as a species have figured out how to use primarily as a fuel for combustion, but then also has a bunch of materiality to it, right? Because we use so much of it so often, we've been trying to figure out how to use this stuff. Okay, great. Got it. But where I'm going to here is there's two things. One, you're solving for a couple different problems. One is, if I look at oil as a substance in all its use cases, is there a comparable substance that I can map against it in all the use cases of oil? And that's one way to look at this, because oil does combustion. It does, some material for plastics. It does other use cases. I'm sure if I created a chart, oil does these 3, 4, 5 things, right? And that are pretty systemic to everything that we do, right? Yeah. And so one challenge is there a material that is out there that can be applied the same in all the different use cases oil can, as efficiently and as effectively as oil can? That's one problem we're trying to solve. Mm-hmm. But then a second problem, which I think is left off the table, which is kind of an interesting one, is we're still predicating all our energy, use case number 2, on combustion and combustion engines. Now, call me silly, but that hasn't changed at all. Right? As I start to move into now electric vehicles and thinking about electric, this is really the first deviation from a combustion engine. Because if I'm just going to explode something to get power, and this is where I get into the particle physics things, I know there's infinitely more efficient particles and compounds if I'm just like nuclear, for example, right? I mean, for God's sakes, nuclear's got a really bad rap, but the physics behind nuclear energy to this day, and correct me if I'm wrong here, you're the particle physics, is like the most efficient as far as generating power is concerned.
You got fission and you got the developments in fusion happening right now. So there's a lot. Right. Yeah. So I had that epiphany in grad school where this was kind of going back to when Tesla basically got founded. I was following Tesla in 2006 when Elon bought him, and it kind of turned. They usually bought AC propulsion, and so he kind of started advertising the Roadster as this high performance electric vehicle. And I remember sitting in our lab telling my other colleagues, hey guys, check out this car. If this is successful, it's going to change the trajectory of vehicles. We're not going to be burning our valuable carbon for energy. We're going to be using a much more efficient system to do it, to convert, basically to make mechanical motion versus internal combustion engine. And so, that's really that was critical in my path. It was like, okay, fuels is not, I don't think the demand for fuel is going to be as high as we think it is long-term, because other technologies are going to surpass it in many ways. The performance of modern day electric cars way outperforms even the high performance gasoline cars. Totally. I mean, the fastest car in the world is a Tesla sedan, right? Basically, right.
And mechanically, let's also talk, even again, this is where I think a lot of people miss out on some of the innovation that's going on. But just like you said, mechanically, an electric vehicle, again, love them or hate them, right? But mechanically, it does not break down nearly as much, right? Everything about it is just more efficient, but yet the combustion engine is so it's almost like people forget the fact that the world runs on this idea of a combustion engine, right? And that's one of the biggest reasons why we still use oil to this day.
Well, let's go back to your comment a second ago, because I want to talk about that for a second. So you mentioned with oil, we get so many important things out of it. We get plastics, we get fuel, we get, specialty chemicals, solvents, all this stuff. Is there an equivalent in a renewable pillar, basically. And I guess the fundamental point that I want to make is that, well, what is oil? Where did oil come from? It's in many cases, the petroleum are ancient algae blooms that have been sequestered in geological structures and have had massive amounts of heat and pressure and time to convert all that biomass into what we now call petroleum.
Interesting.
So in a way, really, we're running the entire society off algae blooms, but from the past. Coal is just forests. Wood, it's more lignin, it's more wood. It's a little bit different than petroleum, but specifically the petroleum, they're linking it to mostly algae blooms from, millions of years ago. So in that regard, if we could produce algae blooms today at the same quantity and at the same, quality, I guess, and have a process like thermochemical liquefaction or these thermochemical conversion processes that apply heat and pressure, really do what the Earth has been doing, but in an accelerated reactor way, which I know people doing this. I worked on this a little bit in college myself. Then we can produce a bio oil, just like I was doing with the pine trees, but doing it with oil, and they're doing it with algae rather, and producing an oil that is similar to crude oil. Now, there are some differences though. What we found was that one of the major differences is that when algae is that old and that buried and has that much time, the oxygen all gets used up. There's really not a lot of oxygen in oil. It's gone. It's been consumed. What we do find in renewables is a lot of oxygen. So when you still have modern kind of living things, they have oxygen in them. If you go and ram that straight through one of these thermochemical conversion processes, you end up with an oil that has a lot more oxygen in it. So that oxygen ends up causing a bunch of problems, causing shelf life, causing oxidation. It's a bunch of problems. So I'm not necessarily an expert in this, but from what I understand, the research and I have friends that are experts in this is that they are looking at different catalysts that can essentially remove the oxygen and produce a crude oil that's more similar to what you'd find in out of the ground. But then the big challenge is that, okay, and this is, I think, where the kind of the rubber meets the road, which is the hard part, is that, okay, I think there's processes and there's some teams around the country and around the world that have been able to show they can take algae biomass or other biomass and make a crude oil out of it. But to really scale that, you need a refinery, you need $1 billion oil refinery. And these startup companies and the oil companies, they're not doing this together. These are typically two different efforts. So the small guys are like, all right, we don't want to use oil. We want to use algae. They don't have access to the $1 billion refinery to really scale it up. And the big guys that are doing it, they're doing their thing. They're maybe dabbling in algae and looking at it from an R&D and from a marketing perspective, but are they really like building that whole thing to move the whole society and the whole planet forward? I don't know. Maybe there's something going on behind the scenes that we don't really know about, but it's been slow, and it's going to take a lot of capital to scale up. Now, I did talk to one of my postdoc friend that I went to school with recently. He was telling me that in India, they were working with some oil companies that were taking the algae and non-recyclable plastic waste, putting it through these thermochemical processes, generating a bio oil, and then blending that with normal crude oil at about 10%. So minor amount, but again, at a refinery. So big volumes compared to what we're talking about in the laboratory. Running that crude oil with this supplemental, bio oil or recycled plastic oil, whatever you want to call it, putting that through a refinery. And then he was telling me that they basically were able to make your normal products with minimal issues. Basically, that oil was compatible with the traditional infrastructure. So then it's like, okay, if that's true, then it's a question of scale. How do we get enough algae at a facility that can actually run this thing at scale? And so, we're working with companies like AECOM, massive global engineering firm. They've got grants with the Department of Energy and the U.S. Army Corps of Engineers and some other private companies. On two things. One, we're working with them on harvesting algae. And then once the algae is produced, they're like, all right, well, we can either sell it to Bloom and we'll buy it and put it into shoes and sneakers and consumer products. Or they're also working on turning it into oil for the Department of Energy with some of these other partners. So some of that work is still going on, but it's going to require some major capital investment. For the Bloom side, what we do and what we saw and how we really have positioned our technology and business is we're the low-hanging fruit. We're directly incorporating the natural algae into these products. So we're not harvesting algae and turning it into EVA or turning it into a plastic or turning it into some specific compound, refining it. No, we're taking the natural algae, the natural protein that's in that algae. These proteins are polymeric by nature, naturally polymeric. And we're using heat and pressure in an extruder to essentially open up those proteins, flow align them with the base polymer, start to get them to kind of play together. And then the algae starts to pick up the properties of the base polymer. So we blend it with EVA, we get something that kind of acts like EVA at the end. And then we just drop that right into the existing supply chain. We bag it, we ship it to the factory incorporates into the product. And for every kilogram of the Bloom pellets that are being used, we clean over 2,000 liters of water in the process. And we capture over its weight in CO2 emissions. So it's about right now, our LCA shows that for every kilogram of Bloom pellets being used, you're sequestering 1.7 kilograms of CO2 from the atmosphere.
And just to be clear, to put a finer point on that, when you say a pellet, your product are these Bloom pellets, which are ultimately incorporated or ground into the materials at the refining manufacturing facility, right? To complete the 100% of the material, right? So 10% or 5% or 20% of it is Bloom algae pellets.
The Bloom pellets are about half algae, half polymer. The polymer is whatever the company's already using. That makes it miscible, makes it compatible.
Oh, I see.
If you use something that's not compatible or you just try to use the algae directly, it doesn't really work, unfortunately. It'd be great if it did. Like, we'd love it. Maybe a lot easier for us.
But in time, but you're also competing against, 80, 90 years of oil, petroleum refinement where they've been working. Yep. I guarantee you petroleum didn't come out of the gate and they figured like, oh crap, let's turn it into plastics. You know what I mean? Like that took how many decades to figure that out and refine it and refine it and refine it and refine it. So, again, the point being here. Okay. So I also want to be conscious of time because I know we can go for hours and hours here. So I want to pull back a little bit to, again, kind of this sort of decision tree. So algae though, and correct me if I'm wrong here, in the history of our exploration, algae's been here forever. And, God forbid, it's probably the foundation of life as we know it, right? So the fact that we're actually getting back to the roots, and I find it fascinating that petroleum, I hadn't even thought of it, is actually algae. It's just been Earth has refined it, right? Over a certain period of time, right? And we haven't figured out how, but in fact, you're going back to the source. You're like, all right, I'm going back to algae, right? So initially though, algae was explored, if I'm in the history of it in the last, say 20, 30, 40 years, as a food, as a fuel source, and now a material. So somewhere in there, you figured out like, okay, people have been hunting for fuel alternatives. People have been hunting for food alternatives. Oh, we actually have a material alternative here because that's a newer, I think, application of algae in a way that's probably in the last like 10 years that people have started to kind of go down that road, or help kind of build the history of that.
Yeah. I think we were probably one of the first. We filed patents in 2009 at the University of Georgia using the algae as a thermoplastic composite. So prior to that, when we were doing all of our prior art research back then, people had been using seaweed in composites. So that was out there, and mostly based on the cellulose. Certainly soybeans. So the protein-rich soybean meal has been used as a composite material in thermoplastics as well as cornmeal and potato starch. And so there was, prior to us starting, there was already, a couple decades of lab and early startup bioplastics. And so the unique angle that we looked at for the algae was that the high protein content, those proteins are polymer chains of amino acids. So the protein is a polymer. And when we first started looking at the algae, it was a quick little story. I was working with a different postdoc from the material science department at the university. He came to our office. He just started the university. And he came to our lab. I gave him a tour, and he had mentioned, hey, by the way, my PhD was on turning turkey and like poultry waste into plastics. So he was taking bone meal, blood meal, and feather meal, all the leftovers that are basically like kind of high protein powders, really, and that come out of the poultry industry. It's a big problem, big waste product. What do you do with this stuff? And he was compression molding it and making little plaques, little bars, little test bars out of it. And so he told me about that. I said, well, that's funny because that high protein content is similar to algae. Algae has high protein as well. It's not animal based, it's plant based. Right. But it's a plant-based protein. Maybe it can work as well. And so I had this big tub of algae that was left over from all of our oil extraction work. That was the 80% fraction that we were trying to figure out what to do with. In fact, it was actually a 93% fraction because we only got 7% oil yield, not 20. So it was even worse. We were more motivated to find an alternative because there really wasn't much oil in this algae when it's being grown in wastewater. And so when it's growing fast, it's producing protein, not oil. So we looked at the protein and I worked with this professor. We got a little compression molding. We did some samples. We made some little dog bones, 100% algae. It worked. It made a little bar. And then we took that little bar and we put it on what's called a dynamic mechanical analyzer. It's basically like strumming it like a guitar string. You put it in a little mount and basically it has a little piece of metal that comes down and vibrates the bar. And as it vibrates, it essentially measures the stiffness and the energy return of the part. So as you deflect it, does it bounce back? If it bounces back, that's a key characteristic that you have a viscoelastic material, also known as a plastic, right?
Got it.
Even though it's not traditionally what we call a plastic in the sense that it's not polyethylene. The problem with it was that it was rather brittle. It would bend, it would come back, but you bend it too far, it would snap very easily. So all the initial samples I had that 100% algae, they're all broken because the second anybody went with their hands, tried to flex it, it would just snap. So I had one of these little fractions of a piece that was my part of the project. I kept my desk as a little memento. I showed it to this local entrepreneur that was helping me with an ultrasonic project as well. And he was from the packaging industry. And I told him, hey, this little sample, I was like, we just made this. We're making like plastic out of this algae somehow. It's kind of cool. And he got all excited. He's like, oh man, he's like, I work for massive packaging companies. I do business with Walmart, Coca-Cola, Pepsi. These guys are all talking in these private board meetings I have, meetings with these companies. They're asking us about bioplastics from a filling packaging company perspective. He's like, if you could produce an algae-based plastic and our equipment could use that as packaging, we could fill it. We can basically connect you with these big brands, and we could maybe work together and start something up. So that conversation evolved. And it's kind of funny because this is ultimately the other co-founder of ALGIX. This is Mike Van Journen. So Mike, I remember Mike was like, hey, Ryan, he's like, we're looking for guys like you in our team. We need smart guys like you on our team. And I'm like, all right, yeah, I'm going to get a job out of college, go work with a big company. Well, turns out it was just him and me. There was no big, it was just like him and me in a garage, basically doing startup mode. So, which actually honestly was better because it gave us a blank sheet. It gave us a blank sheet and we said, all right, let's do this. So once I kind of figured out what was going on, I was like, all right, this is basically straight into startup mode. So I graduated with a master's. I gave up on the PhD, which I was on PhD track. I kind of said, you know what, I'm going to forgo the PhD. I'm going to get into industry. I'm going to go ahead and try the startup world, see how it goes. That was 2010. And so we basically realized we had a pretty far uphill battle, no supply chain, no robust algae supplies, no real customers, no real factory, technology still lab scale, like every headwind you can imagine we were faced against, didn't really have a lot of we were personally wealthy. I was a grad student. I had no money. I was like, money. Right. So Mike was good. He was able to get us some capital. He hired me. I was full time. I was the only guy for 2 years trying to get the whole thing going. We hired a few, another scientist, a chemist, and, some few other people to help kind of get going. And then finally in 2014, we built the factory, which they kind of tell us never to do this, but we did the total, if you build it, they will come. We realized we didn't build it, like no one's ever going to take us seriously.
Right.
And, and we can't and the development of not building it and working like with all these different people, it was so expensive and so complicated, and you're shipping material around. Like it was not so easy. And we did that for a couple of years, but ultimately in 2014, we're like, all right, we just got to bite the bullet and we got to build something. So we raised about $12 million and built this biocomposite facility in Mississippi, and just jumped off the deep end and said, let's do this.
Good for you guys. Well, I mean, hey, welcome to Startup Land. Welcome to being an entrepreneur. So let me dive in a little bit too, because, and again, to be clear here, a lot of people might have heard, and just to get real clear, people think algae or bloom or whatever, algae bloom, and they're thinking fuel, but you guys are actually really looking at materials, right? So it's 100% materials. You are a substitute or an alternative to quote unquote petroleum-based plastics, or an additive to it. And so as of now, because over here it could be fuel, right? Still, right? Like that's someone else's problem to go figure out. You want to go take this material and use it as an alternative combustion source to oil or gas or whatever, feel free. But we're going to work on materials here, because plastics are in everything. What's the single biggest ocean polluting material? It's plastic, right? Yep. What's the thing that we need to figure out how to, recover and reuse? Well, plastics, of course, right? And I mean, here's a fabulous story on how to do it. So today you're in sort of athletic wear. You talked about Adidas. I'm sure you already know this, but Nike, the guy who's running Nike right now, John Donahoe, he was the ex-CEO of eBay. I happened to be there at the time when he was there. He is a massive renewable circularity guy, right? In fact, he was the reason we greenlit a natural gas primary fuel source for our data center in Utah, right? Which at that time, funny enough, the name was Bloom Energy, right? Bloom Energy builds, they're a fuel cell, and they've took a while to build, but now they're kind of everywhere, in fuel cell technologies. But we at eBay were the first actually to decouple our data center from the grid and use just fuel cells and natural gas, right? And it was just a couple cents more, but at these commodity levels, that makes a huge impact. But Donahoe, as the CEO, greenlit the project, even though he knew it was slightly more expensive than our traditional, because he knew it was the right thing to do. So I think you're also seeing leaders show up at companies like John at Nike, or whoever you're working at, Adidas, or whoever else, that are starting to actually make the decisions that are more for the betterment. They see the long term, 10 years down the road, not the immediate quarterly adherence to Wall Street.
So that's a great point. So right now we're seeing the publicly traded companies are under intense pressure by their investors, particularly the private equity groups, the family offices that are putting big money in, and the primary investors, a lot of these companies, they are requiring what's called ESG reporting. So they want you to basically measure what's your environmental performance, what's your social performance, what do those metrics look like? What are you doing to measure and capture your impact, both in terms of like your operation as well as your supply chain? A lot of these companies, like I said, will actually make the products. So you got to look at the office, the design studio, the logistics. Yeah, that's like under your control. That's kind of like a class one. But then when you look at these downstream, other elements, that has to be pulled in too. And so when you bring all that together, the ESG reporting and measurement is great for us because two things. One, it means the big companies, if they don't measure how they're performing environmentally and socially, and if they don't measure it and they don't show improvement on it, the big investment banks are divesting. They have specifically BlackRock. I said, we are divesting out of companies that are not measuring and improving their ESG. It's very, very simple. So when I talk to our publicly traded customers, we have a lot of small brands that are not publicly traded, but our big customers are Wolverine, Adidas, Nike, others, Polaris. When you talk to these brands, it's like they get it. They understand they've got to be pioneering this and be in the forefront and pushing it forward. Because if they're not pushing it, it's going to be pushed onto them. And they'd rather be driving it than having to deal with somebody else, some regulator doing it. And so I think that those reports are really insightful because they require the company to do some due diligence on their impacts.
Yep.
And so it's really hard when you lack transparency in your supply chain. A lot of the brands, not the big brands maybe have a little better feel for it, but a lot of brands we talk to, when it all starts getting made in China, like you don't quite know exactly where this stuff's coming from, who's touching it, how many people are touching it, how old are they? Like there's a lot that goes on that you really can't. It's kind of murky, and so there's a lot of risk there. And so for us in Bloom, what we found our advantage is that we can certify a product that is verifiably better for the environment and measure and track that product through the production of the algae, the conversion into the Bloom pellets, the shipment to the factories, and then the projects with the brand. So we know how many pairs of shoes that brand is going to order with Bloom. We know which factories it goes to. The factories are supposed to give us information back on how many pairs they're producing. We match that up with the brand. And then we can tell the brand, okay, for this season, you clean this much water, you reduce this much CO2 emissions based on you buying 10,000 kilograms of Bloom, as an example.
What a fabulous, but that's, I mean, you just nailed what every, I don't know the sustainability officers or the C-suite at these companies are looking for, right? I need an alternative material, but I also need to score it so I can show my progress, right? Which is a critical piece to this, right? Because, my former life in data centers, we had a little metric called PUE, and that metric called power utilization efficiency really was the inflection point when data centers went from largely inefficient design to super hyper efficient designs, right? But it was one piece of data. And when people started publishing that, scoring against it, you can map exactly that inflection point of drive towards the innovation towards sustainable data center designs. But let me, because I knew we were going to run into this, and I'm looking at the time here, and there's so many things I want to get into. But before I do, I do want to get this one in here, which is, so again, we're talking about materials. I'm going to fast forward a little bit because typically I sort of do a sequence, but I'm going to jump ahead, which is, okay, you guys are an algae, you're providing materials, you're already kind of established, you're putting in shoes, consumers, whatever. But you also talk about pellets, and where I'm going to now is, and we talked a little bit about this, is 3D printing, right? So if I look at where the puck, where the net's going to be, right? If I think about where the net is going to be, one of the big game changers of the next, this decade of supply chain is going to be 3D printing, right? And I'm not sure a lot of people really see that for what it is, but that's going to upend the supply chains as we know it in how and where stuff is produced. And those that are supplying those 3D printers with the powders capable of creating the materials that everyone wants, well, shit, they're going to be winners. Where are you guys in looking at that?
So we started our own 3D printing company. We had it for a few years. We were focused on filament-based FDM style printers. So these are the ones that use weed whacker string that gets melted. So it's a thermoplastic process. Everything that we do is thermoplastics. We were making all of our 3D printer filaments with bio-based and biodegradable polymers, typically PLA, PBS, or PBAT. So these were basically compostable type materials. And then we were blending algae with those to make some different properties. So we did that for a few years. We divested out of that. We still make the pellets, but we don't actually do the downstream stuff. It was just too much for our company to do the whole thing.
Sure. Yeah.
But the idea behind it was really interesting because this started like in 2015 for us when we just started opening up and looking at footwear. So we were still in this kind of shotgun mode, shooting projects everywhere, seeing what kind of stuck. And with the 3D printing, it's a niche market, but it's high value. And you're working with typically companies or innovators as opposed to just like the general public. So it was something that allowed us to for me to reach out to Tesla or me to reach out to BMW or reach out to XYZ company, footwear, even some of the footwear brands. And they have 3D printers. They're printing stuff. So we started, we actually 3D printed a last for a shoe, which is kind of the shape of the orthopedic shape of a shoe that you use to build the shoe around. We 3D printed one of those. So we were looking at it as a way to kind of get our brand, our materials, the concept of algae into these companies at some level, right? So it's kind of like the Trojan horse. Let's get in with some 3D printer filament. Algae's a real thing. I printed with it. I know it's real. I know we can do it now. The filament side was rigid. It was stiff. It was not a flexible foam. That was basically at the same time, our company had a parallel track of foam, flexible foam. And so ultimately the flexible foam, the market size, the customers, just 100 times bigger than 3D market. So we shifted all efforts to that in 2018. So we no longer are in-house directly producing any 3D. However, I will say that we are working with some innovative new factories that are trying to decentralize manufacturing, that are using 3D printing, but in a unique way, as opposed to 3D printing the part, like let's say the sole of a shoe, which some people are doing, like Adi's doing the future craft, where it's the sole is actually 3D printed. Super cool, expensive, takes forever, takes a long time to make the part, right? Instead, this one group we're working with, they're actually using the 3D printing as the tooling. So as opposed to 3D printing the part, you're 3D printing tooling. That tooling basically is the mold that makes the part. So now you can, maybe it takes overnight to make that mold, but once you get the mold made, you can run hundreds of thousands of parts through that mold. Or from that tooling. So basically we're combining kind of the best of 3D printing. Quick changeover, fast. We can quickly print a new part quickly overnight versus 3 months right now for lead time for stainless steel tooling to get like steel molds made. And then we use that with a thermoforming or packaging line that is all about high speed. So high speed molding of components for shoes using the Bloom material as a substrate. And then once you get that part made, you're able to automate that process, get the cost down per unit. And that's really the only way you're going to be able to compete with China is by looking at implementing, rapid tooling processes, innovative manufacturing techniques that are high speed, and automation where you've got a couple people running some HMIs that are basically cranking out millions of pairs of parts. For a shoe, or maybe even a simple shoe, a sandal, a flip flop, a croc style thing. So that's something that we're working on right now.
Cool. All right. So again, I'm sitting here. My head's bursting with all the stuff I want to get to. We're kind of winding out of time here. I want to be conscious of your time and just the whole recording. We're going to do this again because there's so much in here, and I mean, literally. Part of my question there is also just looking forward, saying it feels like you guys are also not a supplier of the material into current manufacturing, but for future manufacturing, you may create a format of your substance that's in 3D printable form. Not actually build 3D printers, but be the wholesaler of wholesalers that is refining this algae in a way that makes it 3D printable. And you're just delivering an indirect model to all these 3D print, let the 3D printing world figure it out. You guys are just sitting here waiting. Hey, we've got a substance that's 3D printable, right? And it's, by the way, it's just 100% renewable, biodegradable, yada, 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 yada.
Yeah. So that's kind of where we're at. We've been sitting in that position for a few years now. We worked with a company called 3D Print Life. They've been kind of taking over that business. They distribute, whenever they need to produce more filament, they contact us. We make the pellets. We pellets. They turn it back into filament and brand it and package it. And so that for us, when we started that, we were responsible for the branding, the packaging, the distribution, the Amazon store, the micro centers, like all that. So we did it from ground up. And through that, we also did a bunch of Lean Six Sigma training internally. So we got green belts and black belts. We did a lot of lean manufacturing. We did a lot of marketing. We did website development. I mean, the whole 9 yards. It was educational, but really tough. It was really hard. Right. Well, hey, again, welcome to entrepreneurship, man. You never know what your job's going to be on any given day, right? You're going to be doing all sorts of stuff. So Ryan, let me wind down a little bit. So what's kind of on the horizon here? I mean, a couple things and whatever you want to talk about, but at the same time, like, it just feels like algae's been around for a while, but we're at this very interesting moment where circularity and sustainability is maybe finally going to take hold, because we've been talking about it for God knows how long, right? But now it seems like you talked about corporate responsibility, investors, public companies. Even I'd go so far as to say it's transparency, because you talk a lot about that, right? There's the transparency. People just didn't know what was going on in our supply chains. And now that people are awake, like blood diamonds, or the thing, it's like, do you really realize what goes into this thing? Right. And so that's changing everyone's buying habits and thinking and what's the right thing to do. But algae, again, is one of these substances. I've heard about algae for decades. So it feels like it's one of those things that's waiting for us to figure out how to use. It's not that it's, it is what it is. We just haven't figured out how to best
go back to the source of what actually petroleum is, which is algae, and use it. Like you're going back to the roots. So what do you see in the sort of next few years? I mean, it sounds like you've kind of crossed a little bit of the chasm yourself. You're in a business that's now got some profitability to it, but the whole industry is shifting in this direction. Like Yeah.
I think the trade wars, the COVID issues, even the Ukrainian war that's recent. I mean, all these things have been horrible for the world. Very, very horrible for the world. But I guess the silver lining is that it has awakened a lot of people to what's really what our sensitivities are. Where's our vulnerabilities?
Right.
And certainly putting all of our eggs in one manufacturing basket is a problem, both from a sustainability perspective and from a transparency perspective, and from just like getting your stuff on time.
Yeah. Right.
So companies are trying to diversify. They're looking at reshoring. They're looking at decentralizing. They're trying to find backup plans. So I think that, algae has a promising future. There's a lot more work to do. I mean, we still can't make 100% algae shoe.
Yeah, right.
We're far away from that. We're trying to just get the basics done. And the challenge that we found is that even the simplest, easiest approach to get algae into products has been met with a lot of resistance and complications around getting that adopted into a foreign supply chain. It's expensive. There's tariffs, there's duties, there's pushback from factories. It's different. It's new. It smells a little bit. There's always little factors that it make it tough. So I think that we're going to see a continued movement towards sustainability. I think it is, like as you said, it is something that is here to stay. I don't think it's going away. I think now it's like, okay, how do we figure it out? The big publicly traded companies that we work with, 2025 to 2030, there's some big goals around using recycled and bio-based materials of the majority of their products. I mean, in some cases, 100% of the products should be produced from bio-based or recycled materials or regenerative materials. So, so that's, whether they're going to achieve that goal in that time frame, we'll see. Because a lot of these times, these are like, this is the CEO or the board saying this, and then that trickles down to the doers, all the people, the product line managers, the designers, the developers, the material and the innovation teams. They now are like scrambling, trying to figure out, okay, corporate set this goal. How in the hell are we going to hit it?
Totally.
How are we going to hit it and maintain our costing and our profitability? Because, one thing for them to say, we're going to do this. It's another thing to say, we're going to do this and we're going to lose 10% margin because of it.
Yeah, totally.
Once that second part comes in, it has to. So they're trying to find. So it's a little bit chicken and the egg. It's scale, right? Like these new technologies, they're more expensive because they're tiny. They're just now starting, and we're tiny. We're a tiny little thing. Tiny. I mean, we did 17 million pairs of shoes. Bloom was in 17 million pairs of shoes last year, but the world produces about 30 billion pairs.
Yeah. Oh no. But the fact that you're even in 17 million is better than zero. Infinitely better than zero. And it is, like you said, crossing this chasm. I mean, people forget, and I know I got to wind down here, and I know we could go for days here. Tesla was bankrupt until Elon literally mortgaged everything in his entire existence to keep that thing going. But it was going to go away. Right. Yeah. And the car industry was hell bent on destroying that, like they destroyed DeLorean and everybody else before it. So, I mean, the headwinds are there, like you said, but it's not incremental. It's a tectonic shift that you've already made in getting to 17 million pairs from zero. Like that's more important than going from 17 million to, a couple billion. I think like that's the
way I look at it is we've already added like 5 or 6 zeros. We just got to add 1 or 2 more.
yeah. But you made the hardest part, Ryan. Listen, I again, like I said, we could just keep going here, so I'm gonna wind it down. But such a pleasure. I hope we get. I want to do another episode. I want to follow up. I think the 3D printing is a super exciting avenue, not to build them, but a material that can be you guys already sit on that simultaneously can be crafted to go into direct manufacturing or into the future of 3D printing. It's a really interesting, but thank you so much.
We're going to see a lot more in automotive and, footwear and consumer products. So I think that's the future for Bloom is mostly footwear, but we are exploring these new markets.
For now, because that material that is used in footwear is used in a gazillion other applications.
Exactly.
Right.
Yep.
Awesome. Well, listen, thank you so much. Been super pleasure. Have a great day. We're going to have a follow-up episode, but this has just been amazing. Thank you so much.
Thank you, Richard. Been great.
Awesome.
Thank you.
Thanks for listening. If you have any comments about this episode or topics on supply chain you'd like us to cover, you can reach us at supplychainnext@requis.com. And while you're at it, check out the Requis platform at supplychain.requis.com. Requis allows you to manage the full asset lifecycle in the cloud while collaborating with your entire value network to buy, manage, and sell your assets. Find out more at requis.com.